In the last video, we noticed that there seemed to be a connection between the injectivity and surjectivity properties and functions having left and right inverses. In this video, we'll make that precise, starting with left inverses. We're going to show that a function has a left inverse if and only if it is injective. So let's begin the proof with the easy direction. Ignore the diagram for now because we'll come to this diagram when we do the harder direction. So we'll suppose first of all that a function has a left inverse. So suppose that your function f from x to y has a left inverse g must be a function from y to x if it's going to be a left inverse, and we want to prove that f must be injective, so we'll suppose that f of a is equal to f of b for some a and b belonging to x. Since I want to prove f is injective, I must show that in this case a is equal to b. And I can do this by simply applying g to both sides of that equation. So if f of a equals f of b, then g of f of a equals g of f of b. But g composed with f is the identity. So because g is a left inverse, what it means to be a left inverse is that g composed with f is the identity on the set x. So what we get out of this, because g composed with f is the identity, g of f of a is just a again, and g of f of b is just b again. So we suppose that f of a was equal to f of b for any two elements a and b in x, and we've proved that a has to be equal to b. That shows that f is injective. Alright, so the tricky direction is the other direction. So we now, to do the other direction, have to suppose that our function is injective and prove that it must have a left inverse. So we have to show that there exists a function g such that g composed with f is equal to the identity on x. So g of f of x is equal to x again for all little x in big X. Let's look at what's going on in the picture here. So we'll begin with something in x. So here is this black dot here is supposed to represent some element of the set capital X. And then the grey line is showing you that what f does, f sends it to some element in y. And because f is 1 to 1, there are no two dots in y which are the target of two different arrows coming from x. That's what it means for f to be 1 to 1. So if you think what g has to do, well, g of f of x must be equal to x for all little x in big X. So I've got my yellow dot on the left-hand side, which is my x, and then over here I've got f of x. And g of that must be the place you started off with, the element of x you started off with. So what g must do to this yellow dot on the right is it must send it back to the dot that we highlighted on the left. So g must kind of reverse this arrow. I'm going to draw another arrow ahead here to say that this going in this direction is what g did. And the same is true for every other arrow, right? What g must do is simply look where f sent an element a in x, and then send its image in y back to where you started in x again. So we've got to add arrowheads going in the opposite direction for g to all of these arrows. But that doesn't completely define a function from y to x. And the reason it doesn't is because there may be elements in y which are not in the image of x. So there's no reason, not in the image of f. There's no reason to suppose that f should be surjective here. We're only assuming that it's injective. So there may be some elements like these black dots at the bottom here which are not in the image of f. And we still have to say what g is going to do with them if we're going to define a function g from y to x. But the thing is, it doesn't matter what g does with them. As long as g does this reversing arrows behavior on the other elements, it'll still be a left inverse to f. So we can send those things anywhere we like. And the simplest thing to do would be to pick an element in x, any old element, let's call it x0 as I've done here, and just say, well, I'm going to send all those other things to the same place, to the same thing, x0. And if we do this, then we've completely defined a function g from y to x, which was a left inverse to f. And the reason we were able to do it was because there weren't two dots in y, which were the target of two different arrows. If that was the case, then we wouldn't have been able to send both of those things back to where they came from, right? We can't send one thing in y to two different things in x if we're going to define a function. Okay, so that's what's going on in the construction we're about to do. We're just going to write down a definition which corresponds to that, corresponds to what we've just been talking about. So we'll define what we're going to do. F is going to be from x to y, and we're going to define g from y to x, which is going to be a left inverse to f by g of an element y is equal to, so we'll have two cases, x0 if y is not in the image of f, and it's going to be x if y is equal to f of x, for some x in x. So where x0 is some element of x that we chose in advance. So it doesn't matter what you choose, you just pick some element. And then this construction works. This is then a left inverse, because g of f of y will be equal to y for all, g of f of x will be equal to x for all little x in big X. So g composed with f is the identity on x, and g is a left inverse to f. Okay, so that's the result for left inverses. Let's now talk about the same thing for right inverses. So we want to prove that a function has a right inverse if and only if it is surjective. And again, leave the diagram for now. Let's do the easy direction of this proof. Let's simply suppose that f from x to y has a right inverse g, which will be a function from y to x. I have to show that f is surjective, so I've got to show that every element of y is actually equal to f of something in x. So let's let y be any element of big Y. Then, what do we know about f composed with g? F composed with g is the identity on y. So f of g of y is equal to y. Okay, y is equal to f of something, namely f of g of y. So y is in the image of f, and we've shown that every element of y is f of something in x. So the image of f is all of y, and that shows that f is surjective. Okay, let's do the trickier direction where we have to show that if a function is surjective, then it has a right inverse. So we need a function g from y to x with the property that f composed with g is the identity on y. And let's now look at this picture which I've drawn of this situation. So the picture I've drawn on the bottom right here, you have a set x consisting of the 5 things, 1, 2, 3, 4, 5, and a set y consisting of a, b, and c. And you have a function f which goes from x to y, and which is surjective. So you can see that the 3 things a and b and c are all in the image. And what we require if we want a function g from y to x to be a right inverse is we need f composed with g is equal to the identity on y. So f of g of y must always be equal to y for each little y in big Y. So what could we do here? I mean, if we've got, let's say we have this particular element a in y. So we need f of g of a to be equal to a again. Now, that means that g of a must be something which f sends to a. So we actually have some choices there. All we need to do is to pick one of the things which f sends to a and use that as g of a. So you can see, looking at the diagram, that f sends 1 and 2 to A. So we could simply send this thing back to 2, for example. That would be a fine choice for G. And then if we look at B, then G of B must be one of the things which f sends to B. So that could be 3 or 4, it doesn't matter which, so we could just send it to 3. And then for C, I've got to send G of C must be one of the things which f sends to C, and actually there's only one here, so I don't get any choices. It's got to go to 5. But because f is surjective, for each element of y, I do at least have one choice for its image under G, and therefore I can use that method just to construct an example of a right inverse to f. So what we'll do is we'll just say that for each y in y, there exists at least one element x in x such that fx equals y. That's surjectivity. So let's say we pick one and we'll call it x subscript y. So in the example that we've got over here, x subscript a would be 2, x subscript b will be 3, x subscript c will be 5. We're just choosing something which f sends to a, and choosing something which f sends to b, and choosing something that f sends to b. So we're making some choices for each element of y. And then we can just define our function g from y to x by g of y is going to be x, y. Okay, then if we think about f of g of y is equal to f of xy, and xy was chosen to be one of the things which f sent to y, so this is y again, and this works for any little y and big Y. So f composed with g is the identity function on y, and that means that g is a right inverse to f.